Okay, hi guys from year 12. We're going to talk today about strain energy. Consider a spring. That's an awful, really bad spring. Let me try again. That's a bit better. Consider a spring where you're applying a force to stretch the spring, and what will happen is that some energy will be stored inside of it, and when you let go, it's going to convert into kinetic energy. It's going to convert into movement. That energy initially stored, as it says up here, as elastic potential energy. And so whenever you stretch any material, it could be a wire or it could be a spring like this one, there's going to be a certain amount of energy stored inside, and that we call strain energy in this part of the course. Strain, you should know, is delta L over L with the symbol of epsilon, the little e. And strain energy is called like that because it's the energy that you get when you generate that stretch, that change in length divided by the absolute length. So here we have that the work done when a wire is stretched results in energy being stored in it, like we just said. But the key term here, I'm going to write it in a different color, and it's the same as the title really. And when that energy is stored in a wire, we call this strain energy. Now, the word work is not one we've used very much yet because we haven't done that part of the course yet. We'll do it next. But in physics, the word work means something very specific. It's not what we mean by work in normal day-to-day life. It refers to any situation where there is a force acting on some object and it acts on it throughout a certain distance. Well, we should call this really, that's okay for now. And so work is obtained by multiplying work as a force by distance. And this doesn't only apply to pushing objects like in that diagram, it can also apply to a wire like this if you're just pulling and stretching it. So the amount of force that you pull with, and this is delta L, the stretch that you put on it, that will also do some work. And all of that work is then converted into the strain energy inside of the wire. So let's draw a little graph. Physics people love drawing graphs. And if we call the y-axis the applied force, so this is like one of our usual spring constant graphs that we've been looking at lately, and that's going to be in newtons. And if we call the x-axis the extension, and that's going to be meters for length as always, then if we look at what happens when you increase the force on a wire or on any material, but here we're talking about the wire, what happens is that as you increase the force, the extension becomes larger. And this is proportional during a certain, for a certain amount of force, but after a while it goes away from proportion. This is not a very straight line, so I'm not going to be able to make my point very well with this, so let's try again. That's a little bit more straight. So that indicates that there is a proportionality there, that the force and extension are proportional during, in between those values. And just at the limit of proportionality here, let's label this force at which that limit would happen. Let's label it F, and the corresponding extension at that force, let's label it delta L. Delta L. Now, so what's happening here? We're applying a force over a distance delta L, and we just said that the work done was really calculated by multiplying the force times the stretch times the distance through which the force acts, right? So the work done then should be F times delta L, right? But that really applies to a situation where the force is constant, where the force is being, is having an effect as a constant value throughout the distance delta L. But so in theory, the equation, if that was the case, would just be work done equals force times delta L. But here, as you can see, the force is not a constant, it's increasing, and so it's changing, it's becoming bigger and bigger. So because the force is changing, we need to take the average force. So you actually take, and because it's a straight line, the average force is just going to be right in the middle. So you can take F over 2 to be the average force there. So actually the more accurate equation becomes for a straight line in which Hooke's law is being obeyed, all of this region of proportionality is Hooke's law, becomes this, F over 2 times the extension delta L. So you can write it normally as 1/2 times F delta L, which is exactly the same thing. You just take the half outside from the F, and I'm getting the letter not very good, that's better. Okay, so then if a question asks us calculate the strain energy for a spring that's doing this, or a wire that's doing this, then you just have to take that value of the force up there and then multiply it in this way and divide by 2, and actually it works out, like I just shaded in there, it works out to be half of a triangle. The area of a triangle is half times base times height. So the base is delta L and the height is F, so the equation is the same. Half F delta L is exactly the same thing as half base times height, right? Now, so we have that the strain energy is half times the tension times the extension, because the tension is the same thing as the force. If you were pulling a wire, then the tension is just the force that's being applied onto the wire, force that the wire is feeling, that's the tension. And so the equation can be said in terms of tension and extension. Obviously delta L is just extension and the tension is the force. So that makes sense. Alright. And now there's a slightly different situation in which you also have to know how to proceed, and that is one in which the material might behave like a Hooke's material, like this, as a straight line initially, but then it curves, and the question might say calculate the work done, or calculate the strain energy stored in the material, which is the same thing as the work done in stretching it, including the curved part. So they're not being nice to us and not giving us just the straight part. They're giving us the curved part too. And so we need to use a different trick. On the one hand, you can, if they give you in the graph lots of squares, you can count the squares underneath to be very accurate, but generally in exams you don't have a lot of time. So what you need to do is to calculate this area that I just shaded, right? But if you can't count the squares, what you can do is this. You need to find the line. This is my first guess. You need to find the line where it could be there, or it could be there, it could be anywhere. But it's try to make it as accurate as possible, obviously, where the key is that this space that I just shaded, which is going to be a rectangle and easy to calculate for its area, it's just going to be base times height. That area, you need to try to make it the same as the one that's actually under the curve. So in other words, this area that you just added on top to what there really was there to start with needs to correspond with this one that you're cutting out. Those two areas have to be approximately the same, and if you manage to do that, then your approximation is going to be very good, and your rectangle is going to have the same area as the graph has under the curve. So probably something like this is a bit more accurate. Maybe this area now looks a little bit bigger than the other one, but So you just literally draw that line and then do base times height. You read off the height from the F that you just drew the line to. You should be markings on the y-axis that will help you to do that. And you calculate the area for the whole rectangle. That will be the approximation to the strain energy, and hopefully those two areas will cancel. So hopefully this area here, which is outside the curve, will cancel with that one which is inside. Okay, hopefully that makes sense. And so in this video we've been talking about strain energy inside of a wire itself, a particular wire, like as shown by this by a graph that corresponds to that particular wire. And in the next video we'll be talking about strain energy per unit volume, and that will be something that you also need to know, and has slightly different maths, but the idea is very similar, and in a way this is an introduction for that. But they're both perfectly simple things and easy to calculate. As you can see, the maths and the geometry here are not very complicated. And hopefully you found this useful, and I'll see you in the next video. Bye bye.